Hello friends, this is Shravan Kumar Manthri. Welcome to our channel CSE GURUS. The next question, that is range sum query. Of course it is mutable, which is given in Leetcode as program number, that is problem number 307. So we'll move on to this and we'll solve this one by using binary indexed tree, or we call it as a Fenwick tree. Okay, we'll see this one first. Okay, we'll solve this one by using binary indexed tree, or we call it as Fenwick tree. Okay, of course there are some methods we have, but we'll see the method. There are some approaches, but basically we are concentrating a best one, that is in this Fenwick tree you will get the complexity as log n for sum and for update also. We'll see that one. So we'll see this concept of Fenwick tree, or we call it as a binary indexed tree, by taking an example, that is range sum query. Yeah, I'll take a problem statement first. Okay, consider the following problem, of course, to understand this Fenwick tree. So what is the problem that we are taking? Range sum query. We'll see what is this range sum query. Of course the problem to understand is very simple. So we have an array of 0 to n minus 1, the elements we have, and these elements, what you need to find, the sum of the first I elements. Of course not only first I elements, you can, of course, sometimes you can take a range also, like first I elements means, let us suppose, what are the sum of first three elements. If I ask you what are the sum of first three elements means, so these three elements, so 2 plus 1 plus 1, which is 4, you can say. And sometimes if I ask you range sum query, like which we have taken right, might be like 2 3 4 5, I want the sum from here to here. So we'll take first how to do this first I elements, and definitely we can get the answer afterwards, like making the subtract of this. Let us suppose, like what is the sum of first 2 to 5 elements, that means the third element to the sixth element. So 1 plus 3 plus 2 plus 3, which is 9, is the answer. So this is 9. For how to get this one, if I take this first I elements concept, so what are the first 6 elements sum? First 6 elements sum is like 12, right? So from 12 I have to subtract till here these two. What is sum? 3. So which you will get your answer, right? So that means if I get first 6 elements, I have to subtract this one. Simply, like, instead of finding 0 to something like I have to find from j to I. So where j to I is the range. Okay, so this is, we can do it if you know simply first the thing like first I elements. Okay, that is what we are trying right now. And not only that, modify the value of a specified element in a particular. So how to modify? So let us suppose I want to modify the element here. What is AF7 file? Let us suppose I want to make it as something like 10. How to do this one? See, all those things we'll see now. So what is the time complexity? We'll get that also, we'll see here. So first we'll take our naive approach. Okay, let us suppose, what are the approaches we have? Naive approach, a simple approach, general approach, and then we'll go for prefix sum. What is this prefix sum? Then we'll go for our concept, which is we are highlighting here, Fenwick tree. So what is this naive approach means? Initially what we'll do is, let us suppose I want sum of the first I elements. Let us suppose first 6 elements. What you have to do, you have to take each and every element. I have to increment sum, is like sum equals to sum plus a of I. This is a general method we know, right? Yeah, sum is initialized to 0 initially, and then every time you have to get the sum, and finally whatever the sum you are getting, that is a sum that you will get it. So this is a naive approach. And what is the complexity that you will get here? Let us suppose I want to find the last element. So you have to go for last element. If there are n elements to be summed up, so the complexity you will get it as big of n, right? Yeah, at worst case you have to sum up all the things, you have to traverse the loop for each and every element, right? So that is a complexity you will get for big of n if you go for naive approach, like taking each element one by one. And what about update? So let us suppose I want to update in AF7 as, like, instead of 5 I want to update 10. So is there any need to traverse every element? Not required, right? Directly I can go to that element and I'll update there. Simply, like, what is a of I, something value if I give, what is I previously, something I'll give, and now I want to update directly. I don't want to traverse each and every element. That can be done in big of 1, right? Yeah, wherever, if you want directly, you can go to that and you can update it. This is fine. Over. Now what about the second one, prefix sum? What is this prefix sum? So that is like I have to maintain an array where I want to store sum of first element, sum of first two elements, sum of first three elements. It's like this. So prefix sum. You can see how the array will be like this. You can see. So here's 2 means first element sum. Only one element. So in here you can see 1. Pf of 1 means 3 means first two elements sum. 2 plus 1, 3. Next here 4 means 2 plus 1 plus 1. Next here 7 means sum of first 4 elements. Next here 9 means sum of first 5 elements. So like this I can maintain, right? So if I go with this approach, so this is, we call it as prefix sum approach. So whenever you take an index 7, so what is Pf of 7 is 21 means, so first 7, or of course index starts from 0, right? The sum of first 8 elements is 21. You can observe, you can add, you will get 21. So this is another approach. And what is the complexity here? You will get it. Okay, let us suppose if I want to get the sum of first 7 elements, first 7 elements means 0 to 6, directly I can get the sum, right? No need to add one by one element like this. So directly I can get the sum. That means the complexity is big of 1, right? So you are not supposed to add all the elements one by one here. Already you added and maintained an array, right? When you want to update, now this is, you can observe. When you want to update, how to update in this array? Is it directly can you update? Not right. Like let us suppose I want to update a of 7 as 10. So where you want to update? Will you do here as 21 plus 10? Will it be okay? Definitely not. Why? Because if this is changed to 5 to 10 means the next elements all must be changed, right? Everything. Let us suppose if I want to change, let us suppose here it is 2. I want to update it as 5. That means whatever the next element sums will be added plus 3, right? So here previously 2 plus 1 3, but now it will become 5 plus 1, right? Here you need to take it as 6. Here you need to take it as 6 plus 1 7. Next you need to take here as 7 plus 3 10, like this. Is that right? So this is what happens when you take for prefix sum. So when you want to get the sum, that is fine, that is big of 1, but when you want to update, in worst case it will be big of n. So like this you can get it. So two approaches like this you have, and if you go for naive approach, sum is going to n and update is big of 1, whereas prefix sum big of 1 and sum is big of n. So if I combine these two approaches, mostly you will get it as big of n approach here. If you want to do here also, is there any method we can do both operations in log n method? So both operations can I get in log n? Yes, the answer is Fenwick tree. So in Fenwick tree you can get the answer, you can get sum in log n and update also log n. Of course you have to maintain the array. In Fenwick tree index array, that has to be maintained for each and every element, but when you want to get the sum you will get in log n. When you want to update, anyway first initially you may have to do for n, all those elements you need to have a Fenwick binary indexed array, but afterwards when you update, always it takes log n. When you want to get the sum, always it takes log n only. We'll see that one first. Okay, how to do that one we'll see. How the Fenwick tree can be taken, again I have taken the same example. How we need to approach we'll see. Anyway, this is the final binary indexed tree array we'll get when you go with Fenwick tree. I'll explain step by step how we'll get value as here 2 3 1 7. Okay, I'll take the reference here, that is a prefix sum. You will get like this. Anyway, I explained this one how it can be done, and for this one I'll show you step by step how it will be. Okay, and how this can be done we'll see. Yeah, so it's a binary indexed tree where it takes the index values in terms of binary. The approach is purely with the binary representation of a in decimal index value. Let us suppose 2. What is a binary value? 0 0 1 0. Let us suppose 6. If I take 0 1 1 0. So according to this binary representation we have to proceed. I'll let you know how this can be done step by step. You can see here. Okay, yeah. Anyway, let us suppose the elements you want to get the sum, first element, second element, like this we are pronouncing. So that's why I'll take from 1 only, index 1 here. So I don't want to take this part. Okay, of course don't confuse here. I'll take a AR of 0, but I don't want to take this value. Okay, so this 1 means which stores some value where you can see what is bt of 1, what is bt of 2. Here it's not like if I take what is bt of 5 means it takes the sum of first 5 elements. It's not like this. That will be done in what you call as prefix sum. Here it is not like this. Anyway, how to do this one I'll explain. Afterwards you will come to know how to calculate the sum, how to get the update also. So initially all the values of bt are zeros. Okay, the array bt are zeros. And now how the approach will be. So first I'll take the one which the first element. Yeah, I'll first go for the first element. What is the binary value of first one? What is the binary value of first one, which is 0 0 0 1 something 1. So now what I need to do here is check it out, what is the rightmost bit, that is set bit. Set bit in the sense which is the bit 1, where you will find bit as 1. From right to left you have to traverse, you have to find out where is the bit 1. Is it in 1's position, 2's position, 4th, 8th, like this. So now it is in 1 position. Okay, anyway, first you have to add, you have to keep the value 2 here, the value of first element which is there in a of 0. First you have to keep here. Anyway, after this what you need to do is you have to check it out, what is the rightmost set bit. 1 is there, so if it is 1 then add 1. Okay, so I'll let you will come to know how this has to be proceed. If it is rightmost set bit is 1, okay, let us suppose rightmost set bit is like this, 0 0 1 0 means here it is, so add 1 0. So like this, so here it is rightmost set bit is 1, so that's why I'm adding 1. So 0 0 0 1 plus 1, which will become 0 0 1 0. What is 0 0 1 0? Which is 2. Go to the index 2, and there also you keep, already it is 0 0 plus 2, now it is 2. Okay, now what you need to do, so where is the set bit? Here it is, add, that is 1 0 means again add 1 0. So this will become 0 1 0 0, right? So this will become 0 1 0 0. What is 0 1 0 0? 4. Go to 4. So where is the 4? Yeah, this one it is 4, right? Yeah, actually this is 5, right? Yeah, this is 6, this is 7. Now this is here where I need to go for, don't go for 3. Why? Because you can see 0 0 1 0. What is the rightmost set bit? 1 1 0. So add 1 0. So I'm going to 1 0, adding 4. 0 1 0 0 means 4. So I'll go for this and I'll keep, that is 0 plus 2 2. Now what next we need to do? Until you need to reach the last element, you have to go like this. From rightmost, what is the rightmost set bit? 1 1 0 0. So here it is 1 0 0. So 1 0 0 you add. So what it will become? So 1 0 0 like this. So then it will become 1 0 0. Is that right? So 1 0 0 means 8 you need to go. So where is 8 here? 0 plus 2 2 here you have to keep. That's it and done. Anyway, you may add 1 0 0, but it will go like this. Is that right? So but this is, what is the value? 16. Are you able to get the element 16 here? No, stop here. Okay, you have to reach up till n value. Okay, if you are 16 means n value is only up till 10, right? So it is exceeding, then you can stop here. That is over. Now the next part, taking the next element. First element is over. Taking the second element, what you need to do? Here you have to come. So what is the second element value? 0 0 1 0. So what is the value here? Second element, of course, index at 1, second element 1 is there. Add here. What is 2 plus 1? Which is 3. First you add 3. Now what is the rightmost set bit? 1. So add 0 0 1 0. So 0 1 0 0, which is 4th position. So here what you need to add? 2 plus, what is the value we got here as 1. So 2 plus 1, which is 3. Okay, now what you need to do after 1 0 0? Add 1 0 0. That means after 4 you will go to the 8. So add like this. So here also 3. Like this we need to get it. Now the next part, after 2 go to the 3. So what is the 3? Now you will come to know exactly the difference. So for 3, 0 0 1 1. Now what is the rightmost? Anyway, first I need to add, what is 3? Index 3, I mean third element, 0 1 2, right? Third element means 1. I'll write 1 here. Now what is the rightmost set bit? It is this one or this one? This one, right? So 1 is there, so that's why add only 1. It's not 3, it is only 1. So now it will become what? For 3 plus 1 which is 4, so 0 1 0 0 you will get it. So that means now where you need to move? 4. It's not like 3 plus 3 which is 6. Only rightmost set bit you have to consider, not all the bits. So 1 0 0, fourth position you go. So this is fourth position, already it is 3. 3 plus 1 which is 4. Now after 4, now what is the rightmost set bit? 1 1 0 0 you have. So 1 0 0 you add, go to the 8th position. So 3 plus 1 which is 4. Right? So like this. So that is over. Next you have to check for the next 4th one. Already it is 4 is there. Go to 4th one. What is the value? 0 1 0 0. Right? So what is the rightmost set bit? 1 is there. 0 1 0 0 which is 8. So go to the 8th one. So 4 is there. And what is the value you have here? 3, right? Anyway, we have to add 3 right here in 4. So 4 plus 3 which is 7. And here also you will get it as 7. Now the thing is, next you have to go to the 5th one, which is the value here is 2. Now first you add 2 here. Now what you need to do here also you will come to know 5 means 0 1 0 1. So 1 0 1. Now what is the rightmost set bit? Here 1 is there. So 1 you add. So it will become 1 1 0, right? So only 1 you have to add. So 1 1 0. So what is 1 1 0? Which is 6. So go to the 6th one. What is there? 0 is there. So 0 plus what is the value right now? You got 2. So 0 plus 2. Now you have to update here. So like this. So after this, what is the rightmost set bit? 1 is there. So 1 0. So 1 0 means, so 6 plus 2 8. So it will become 1 0 0 0. So 8th position. Go to 8th position. 7 is there. 7 plus the value right now we got here as, what is that? 2. 7 plus 2 which is 9. 9 you will get it. So that's it. Okay, again rightmost set bit is 1. Okay, that is 1 0 0. 8 plus 8 which is 16. It is exceeding, right? Now go to the next element, 6th element. So 6 here it is. What is the value? 3 here. Okay, anyway index starts from 0. You have to check it out. Here index 5 means that is 6th element. So going to here 2 plus 3 which is 5. 5 is there. Now check it out. What is this 6? 6 means 0 1 1 0. So what is the rightmost set bit? 1, right? So add 1 0, right? 0. So it will become 6 plus 2 which is 8, right? So 1 0 0 8. You have to go to the 8. And how much you need to add? 3, right? So the value 9 plus 3 which is 12. So now if I go with the rightmost set bit, 1 is there. 1 0 0 which is 16, which is exceeding the size of the array. Okay, we are not going to that. Next element, 7th element. So for 7th element I am writing here, what is that? 0 1 1 1. So now check it out. What is the rightmost set bit? 1. So only add 1. So that's why it will become 0 1 1. Of course, sorry, it will become 7 plus 1 which is 8, right? Anyway, first we need to update here. Okay, what is the value here? You have to update 7th position. The value is 4 here. 4 we need to write here, and then we have to go for the next one, that is 8th position. And what is that? 12 is there. 12 plus 4 which is 16. Now after 16, anyway we will know that 8 plus 8 which is 16, which is exceeding, which we know. So now this part is also over. Now the next one, 8th element, which is index at 7. So here 8th element, what first we need to do? 8th element means index is 1 0 0 0. I'll write here 1 0 0 0. So that last first we need to add that value. What is the value? 5. So 16 plus 5 which is 21. 21 you are getting. And then if I go with the rightmost set bit is 1 only, 1 0 0 0. If I add, it will go till 16. It is going to 16. So that's why it is exceeding the size. So no need to update anything. Now come to here, that 9th element. What is the 9th element value? 1 0 0 1. Now anyway, first we need to add the value. What is the value here? 6 we need to add first. Then what is the rightmost set bit? 1 is there. So add 1. So it will become 1 0 1 0, which is equals to 10, right? So that means in the 10th position also you need to add, right? So 10th position which is inside, right? So that means, so 0 plus what is the value? 6. So here you will get 6. Now the thing is, next, that is over. Of course, if you add 1 1 0 1 0 1 0 then 1 0, what it will become? So it will be 10 plus 2 14 12. Of course it is exceeding, that is over. Now the last element which is in the 10th position, anyway I can add what is there, 6 here it is 7. So 6 plus 7 which is 13 I can add. Of course for 10 also I'll take, where I'll take here, I'll take 1 0 1 0. What is the rightmost set bit? 1. So 1 0 here. So it will become 1 1 0 0. So which is exceeding, anyway 12 which is exceeding. Now you can see what are the values you are getting. 2 3 1 7 2 5 4 21 6 13. Can you check it out where I have shown these values? Yeah, so almost we got it the same thing like. Okay, so like this we'll get the values 2 3 1 7 2 5 4 21 6 13. Now of course to make like this it may take n, of course might be in n times. Okay, this might take, but the thing is, when you want to update it takes log n, when you want to go for sum also it takes log n. Okay, so once you can construct the tree, then no need to do every time to construct for every element, right? When you want to update, so what you need to do, anyway I'll let you know those things also. So the logic here you can see, anyway to update or initialize, first you need to go for the index starting from 0 if possible you can take, and every time you are going with the BD of index plus value, the value in the sense which is the value in a particular index. If it is a of I, so what we have done initially, if it is array, first we added this value, right? So first we have taken this value, then we proceeded with the binary index value, that is taking the set bit from rightmost, right? Yeah. So after keeping the value, how to get the next? Let us suppose what we have done, I have taken 0 0 0 1, then what is the rightmost set bit, means I got it as 1. How to get this as 1? By taking this formula. This formula will work out. So index plus equals to index, and means this is a logical AND operator you can get, or else you can write this one also, it works. So index equals to index minus 1. This is also fine, and you can try any one, so you will get this one, logical AND operator. So set bit, let us suppose if I have 0 0 1 0, so what is the last set bit value? 1, and the 1, right, here in 2 position. So this, how to get this one? So you can apply this one directly, you will get that answer. Okay, so this is what the, and then you are going to that and again adding the value, like 2 you are taking here, sorry, in this not here, you are taking 2, then getting the index plus value which is 1 0, and you are adding and going to this one, next value, what is that? 1 0. So here you are adding, so next you will get 1 0 plus 1 0 4, so you are adding here. So like this you will get the value. So this index means what is the next you will get if I make it sum, so that value you can get it. So index and index means this value you can get it, and anyway plus equals to I have kept, so previous index plus this one value you can get like this every time. So this is what the logic you can take, and anyway you can see here how to get like this, we can get it. And let us suppose if you want to, okay, anyway first we'll go for sum, then we'll come to here. Yeah, how to get the sum? Anyway we constructed a binary indexed tree, which is a Fenwick tree. Fenwick tree we call it as binary indexed. Okay, yeah, now this is a, these are the values you got it. So how to get the sum? How to get the sum? Anyway I have taken this prefix sum array, this is a prefix sum array where I have taken the reference. Let us suppose if I do what is sum of first 7 elements. First 7 elements means I need to start from here up till here, right? So first 7 elements sum I need to get. What is that value where I'll get here in this? I think that is 16, right? That's why I have taken this reference. 16 will get it. This is a free prefix sum. So let us see whether we'll get 16. So here you can see how to get that one. You can see for sum, to get that first you need to go to what is that 7 means, I'll go here 7. What is the value here? 4. So I want to get the sum of first 7 elements. So first I'll go to here, what is the value? 4 plus So I'll go to here 1, that is a what is the binary representation of 7. Now I will check it out. What is the rightmost set bit here? What is that here in one index, right? So I'll subtract 1. Okay, if the rightmost set bit is here, I'll subtract 2, right? So like this, 7 for that. What is the rightmost set bit? 1. So 7 minus 1, which is 6, right? So I'll go to 6th one. What is the value? 5 plus 5. So now again remove this set bit. What is the value? You'll get 100, which is 4. Go to the 4th one. What is the value? 7. So now all set bits are over, right? So that's it. So 4 plus 5, 9 plus 7, 16. Yeah, our answer is correct. Okay. Yeah, let us suppose you could take another example. Which one will take? Let us suppose 5 will take. Okay, what is sum of first 5 elements? So here it is 2 readily available. 2 plus, what is that? 0, 1, 0, 1. So what is the rightmost set bit? 1 is there. So subtract 1. So from 5 subtract 1. What is 5 minus 1? 4, right? Anyway, you remove this one, first one. So if I remove this, it will become 4. So go to the 4th one. What is the value here? 7. Now after removing this, what happened? 100. So this part has removed, right? 4 also, this set bit also removed after adding. So 2 plus 7, which is 9 only. So you can see the sum of first 5 elements is 9. Let us take another one. If you want, you take only 9. Let us suppose. Okay, first 9 elements. What is the sum? 27 you have to get. Let us see how to get 27. What is the 9? 1001. Okay, anyway, first I'll take this one. Sum of 9. First 6 will be taken plus. What is the rightmost set bit? 1. You subtract 1. What will be the answer? 100, right? Which is equals to 8. Go to the 8th position. What is there? 21. Now you subtract the next set bit 1. So subtract this, will become 0, right? So 21 plus 6, which is 27, which is our answer. So that means you can observe here, how you are getting the sum. Is it with n elements or with log n elements? You can see, you can observe. Let us suppose if I want to get the sum of first 64 elements. First 64 in the sense which is 2 power 6, right? So 64 elements, what I need to do? I need to go to the index of 64. Then I need to go to index of, like you can observe, 32. Then I go to the index of 16, right? So every time you can say, if I want to go for 8, okay, 21 you are getting directly. So sorry. So if it is 64 directly, you can get the answer as 64. But if I want to go for 63, if I want to get the answer from 63, I have to go for 63 means you can take your 1, 1, 1, 1 like this. Yeah, like this you will find here, right? So what I need to do when I want to get for the sum of 63, I need to subtract this one. It will become 62. Next I'll go for 60. Okay, then I'll go for 56. Then I'll go for subtracting. So here I subtracted 2, 4, 8. I need to subtract. I need to come for 48. Then I need to subtract 16. Then I'll go for say 32. So then I'll subtract 32. Then what? 48. 16 is over. Then subtract. That's it, over. 32 minus 32. So that means you can see, if I take 6, I am getting the answer in 6 steps. That is 2 power 6 means 6 steps. That means if there are 64 elements, then I am getting the answer in log of 64 base 2. So if I have n elements, I'll get the answer in log n base 2. So this is what you can find the sum in log n only. So the logic here you can see, observe index plus 1 every time. You can see if till index is greater than 0, that's what sum plus equals to whatever the initial value you have, that has to be taken first. Then index and minus of index. So that's what. Let us suppose if I am at index 7. So in order to get 0, 1, 1, 1, I need to subtract 1. So how to get this 1? From this one only, and then subtract. So you will get 1, 1, 0. Going to the 6th position and take the value. Next from this 1, 0, that is you will get it from this one. Subtract, you will get 1, 0, 0. Next you will get this one, subtract 1, 0, 0 until you will get it as 0. So finally returning the sum. So this is what happens when you go for sum. So where you will get the complexity as log n. Now I'll go for the update also. Let us suppose if I want to update something. Let us suppose I want to update the element at 4th position, which is 3. I want to update it as something like 7. So 4 will be added. So where I need to update in binary index tree, that means going to the 4th position, I have to add here. First. What is that value? Extra value you are getting in the 4th position, the value which is whatever the value you have here, that has to be updated. Then 8th position, then 16th position, then 32 position, like this, not the middle elements, right? So let us suppose if I take 5, if I take the index 5 in 5th element, I have to update at 6th element, 8th element, 16th element, like this. Whereas if you go for prefix sum, you have to update each and every element, right? If you take in prefix sum, let us suppose if I want to update in something like second element, if I want to update here, I have to update every element, the next consecutive elements. Whereas if I want to update in binary index tree, here if I want to update, I can update at the 2nd position, 4th position, then 8th position, then 16th position, which gives the complexity as log n only. So that is what here we can say the complexity for Fenwick tree to get the sum, which is log n, and for this also update also you are getting it as log n. I hope you understood about this one, about getting the Fenwick tree, concept of Fenwick tree, as well as how to get the sum of first I elements. Yeah, one more thing we forgot here. Actual our problem is range sum query, right? So that means we got the answer from first I elements, right? So let us suppose if I want to get the sum of, I'll go here. Here I have taken what is sum of first 9 elements. What is the answer? You got 26. What is the sum of, let us suppose 5 elements is 9 we got. Let us suppose I want to get from 5 to 9. This is we call it as range sum query, right? I want to get the sum from 5 to 9 only. Okay, 5th element to the 9th element. What you need to do? Simply whatever the sum you are getting of 9 minus this one, right? Yeah, we can take here, like let us suppose if I want to get j minus I. So what you need to do here is sum of j minus sum of I minus 1 we have to take, right? So I minus 1 we have to take. Let us suppose 5 to 9. What you need to take? Sum of first 9 minus sum of j minus I. I minus 1, 5 minus 1, which is 4. Okay, sum of 4 elements you have to take. First 4 elements, what is the sum? 7. Okay, first 9 elements, what is the sum? 27. 27 minus 7, which is 20. So like this you need to check it out, the answer. So this is what about Fenwick tree and how to get the range sum query values. I hope you understood the things, and we'll see the next question in the next video lecture. Thank you.